Our final lesson on regression discusses the topic of logistic regression. When our response variable is one with only two choices, we call it a dichotomous response. Examples are yes or no responses, true or false, up or down. You may also see or hear this type of variable referred to as a binary response. When we have a dichotomous response, we can use logistic regression to model the outcome. Note that the dichotomous response values are categorical. To use logistic regression, we will re-express the two possible values using the numbers 0 and 1 to make them quantitative instead of categorical. To understand logistic regression, we need to understand the odds of success. Many people mistakenly believe that the odds of something occurring are the same as the probability of something occurring. This is not true, but odds and probability are related. Specifically, the odds of success are defined as the probability of success divided by the probability of failure, or P divided by 1 minus P. Note that we use the Greek letter theta to represent the odds. Suppose the probability of my making a shot from the free throw line in basketball is 20%. I'm much better at watching basketball than playing it. What are the odds that I make a shot from the free throw line? We first identify a success as making a shot from the free throw line. P, the probability of success, is 0.20 or 20%. Plugging into the formula for odds, I calculate a value of 0.25. So my odds of making the shot are 0.25 or 1 to 4. Note that probabilities go from 0 to 1, while odds go from 0 to infinity. An event that is just as likely to occur as not to occur have odds of 1 or 1 to 1. The more likely the event is to occur, the higher the odds. In a study of esophageal cancer, scientists collected data on the size of the tumor the patient had and whether or not it had spread or metastasized to the lymph nodes for 31 patients with esophageal cancer. The scatter plot displayed here shows the data. Do you see a pattern in the data? Look for the typical size of tumors that had not metastasized and the typical size of tumors that had. The data suggests that, in general, larger tumors metastasize more often. Can we use simple linear regression to model these data? Does fitting a line do a good job of describing this apparent relationship? Of course not. Not only does the line not fit the data, but the predictions wouldn't make sense. What is 1/2 tumor metastasis? So linear regression does not make sense here. Here's another idea. We could split tumor size into categories of small, medium, and large, and conduct a chi-square test of independence on tumor size category versus metastasis. Well, we could do this, but we would lose the precise information about the tumor size by categorizing this variable into broad buckets of size. So what is a better idea? We can re-express our dichotomous response variable using 0 and 1 and carry out a logistic regression. The logistic regression model will fit an S-shaped curve to our continuous predictor to predict our binary outcome. We want to use logistic regression to predict the probability that a tumor will metastasize based on the size of the tumor. Or we may want to predict the odds. Remember that odds are directly related to probability. Tumor metastasis is our binary or dichotomous response, and tumor size is our continuous predictor. When we fit a logistic regression model to these data, we will get the S-shaped graph you see plotted here. How do we get this model, and how do we use it to calculate probabilities and odds? R will do a large amount of the heavy lifting for us, but we will still need to do some lifting ourselves. Hold on to your hats, folks, because the next few minutes will involve math. Pause this video if you need to, grab a refreshing beverage, get comfortable, and then press play again to give me your focused attention for the next 5 minutes. Let's start with a model we know, the linear model, y equals beta naught plus beta sub 1 times x. Remember that our response variable, y, is tumor metastasis, a binary outcome. If we use this linear model to predict y, we will get a value with no interpretable meaning. 1/2 tumor metastasis, for example, makes no sense. Our solution is to replace y with the log odds of success. This is our regression equation for the logistic regression model. Note that estimation of the parameters in this model is not the same as for simple linear regression. The specifics of this method are beyond the scope of this course. Now that we have our regression equation, we want to put it in terms of odds rather than log odds so we can make practical predictions on the odds of success. Remember that in statistics, log refers to the natural log, or ln. So to get our equation in terms of odds, we exponentiate both sides of the regression equation. Doing this gives us our equation in terms of odds. So we see that we can estimate the odds of success at a given value of x with e raised to the power of beta naught plus beta sub 1 times the value of x. Now let's express our equation in terms of probability of success. First, to make the algebra a little simpler, we will set the right side of the equation to y. So now we have p over 1 minus p equal to y. Next, we'll do a few steps of algebra until we get p of x on one side by itself. But remember that y is a placeholder for e to the power of beta naught plus beta sub 1 times x. Plugging back into y, we get our formula for estimating the probability of success at a value of x. The final result we will find is the odds at x plus 1 relative to the odds at x. This will tell us how the odds change when x increases by 1. Recall that the odds of success at x is equal to e to the power of beta naught plus beta sub 1 times x. Plugging in x plus 1 for x gives us the numerator, and the denominator is simply the odds at x. A few steps of algebra to simplify gives us e to the power of beta sub 1. We now have formulas for the regression equation, odds of success, probability of success, and the change in odds when x increases by 1. Notice that each formula is stated in terms of beta naught and beta sub 1, which we will find in the R output of our logistic regression. To run a logistic regression in R, see the code at the top of this slide, where y is the dichotomous response and x is the continuous predictor. The coefficients table gives us b naught and b sub 1, which we then plug into our regression equation. Plugging into the formula for probability at x gives us the S-shaped curve in the graph. Let's estimate the probability of metastasis for a tumor of size 7 centimeters. Because we are estimating probability, we will plug b naught, b sub 1, and x equals 7 into the formula for p. Notice that we call the result p hat because we are estimating the probability based on a sample of cancer patients, not the entire population of cancer patients. We estimate that a 7 centimeter tumor has an 81.7% chance of metastasizing. Suppose we want to know how the odds of metastasis change as the tumor grows. We will use our formula for odds at x plus 1 over odds at x. Plugging in the value of b sub 1 gives us 1.67. Remember, this is a ratio. We say, with each centimeter increase in tumor size, the odds of metastasis are 1.67 times the previous odds. Or we could say the odds increase by 67%. The logistic regression with one predictor can be generalized to more than one predictor by adding linear terms to the right side of the equation. As this is a form of multiple regression, remember to make interpretations for a predictor after accounting for the other variables in the model.